This is a lesson on compositions of transformations. It'll be 2 reflections. We'll start with reflections over parallel lines. So first we'll have 2 parallel lines. You can do this with me. Start and make our random triangle. So pick a triangle out over here. And this triangle I think will be dog. We'll name it. Triangle dog. We'll reflect triangle dog across the first line. Don't have any reference here to the coordinate axis, so we're going to count to get to it. We'll remember that a reflection in a mirror, the line of sight will need to be perpendicular to the mirror line. So we'll keep along here. We'll count 3 from the mirror, 3 from the mirror, because it's equidistant. Remember from last time that the line of sight is bisected by the mirror line, so this will be O prime. Then D prime will be straight across perpendicular, the same number 7 across, so there's D prime, and then G prime. We'll make dog prime, there we go. After we've made dog prime, we can see that it looks like a reflection in it. We can see the lines of sight which go along here. They're perpendicular to the mirror line, and they're parallel to each other, as is usual in reflections. Having done this, we'll now reflect dog prime across the second parallel line to form dog double prime. We'll keep with the same lines of sight. And we'll get dog double prime. Now when we look at this, we notice a remarkable similarity to dog and dog double prime. They're the same. And if we actually just ignore dog prime, we look at dog and dog double prime and say, how do I get from dog to dog double prime? I say, oh, well, that's a translation. It's just a slide going across. But it was created instead by 2 reflections. Let's see some more characteristics of that. First off, count how far it is from dog to dog prime, double prime on a corresponding vertex. So for example, from G to G double prime, when you count it, you'll see it's on this grid, it's 20 units. Notice that the mirror itself, the 2 mirrors, are 10 units apart. What do we have here? We have 2 reflections from mirrors that are 10 units apart. Oh my goodness, the result is 2 figures that are 20 units apart. So 2 reflections in parallel lines. The parallel lines are 10 units apart. The result is a translation that's 20 units. That sounds like a theorem. And indeed it is. Here it is. Oops. Given two parallel lines, a reflection over the first, then a reflection over the second is the same as a translation from the first to the second, from the original to the second copy. A line connecting corresponding points is perpendicular to the parallel lines, and the distance between corresponding points is twice the distance between the parallel lines. The next one we'll do is a reflection with lines that are not parallel. So we'll start with just a line. And we'll draw us our random little triangle down here. I'll just put it there and there and maybe there. This one will be cat, I suppose. So here is triangle cat. Now reflect triangle cat over the line. Now notice we don't have the handy perpendiculars that we had before. The line of sight is still going to have to be perpendicular to the mirror. Here's the mirror line. The lines of sight have, from each individual vertex to the mirror, have to be perpendicular. Well, we're just going to do the cheap and dirty version, try to figure out a way to do it with what we've got, and do that by taking your ruler and placing it so the best you can tell it's perpendicular to the mirror line. Then look on the ruler. I'm not going to ask you to use a ruler to measure much in this class, so relish it this time. The same units across to make for the reflection. So this will be A prime. Do it for the others. Get it nice, as perpendicular as you can get it. So there's cat prime. Cat and cat prime. Now we're going to reflect it again. We're going to need to do a third triangle. Just any angle here. When you draw yours, make sure there's room on whatever graph paper you're using to reflect it across it, because now we're going to reflect across this intersecting line. I'll do the same thing. My lines of sight need to be perpendicular to my mirror line. I'll put it so it's perpendicular, then mark the same distance on the other side and label it double prime. And draw cat double prime. So there's cat, cat prime, and cat double prime. That looks pretty much like, well, let's see. It looks like it might be a rotation to me. So what I'm going to do is I'm going to treat it like a rotation. A rotation is always about a particular point. Just like on a clock, you got the hands in the middle and they rotate around the center. Rotation will always have a center of rotation. And so just choose any one of your vertices, doesn't matter. I'm going to choose A because it's convenient. Draw a line to the proposed center of rotation, which is the intersection of the two lines that we've drawn, and do that for all of the A's. Take a piece of patty paper or a piece of plastic and do what I'm doing here, which is to show how it works out. We'll see how good I did. Here's cat, the original, and my reference line going to the center of rotation. Then I'll rotate it. And notice when I rotate to cat prime, that doesn't work. I'll rotate here to cat double prime and see how, oh hey, I did pretty good. Okay, when you do it, depending upon how good your perpendiculars are, it may or may not be quite this good. This one turned out unusually well for me. It's not perfect, but it's close. It's good given the particular equipment that I have here. So what I see is that a reflection once and a reflection again over two intersecting lines has the same effect when you ignore the middle one as being a rotation. Well, I wonder how much that rotation is. Okay, rotation, we're going to measure in degrees, like an angle. So we'll get a compass, a protractor, and I'll measure these two angles, the ones that I created. Again, the rotation is always about the center. So where we measure the rotation is at the center of rotation and not on the figure itself. So I'm going to show it as about 73 degrees and about 18 degrees. So that's a total of 92 degrees. Pretty close to a right angle. That would be my total rotation from the original to the second copy, cat prime. Now, if you would please figure out how much angle there was, what was the measure of the intersection of the two intersecting lines. To do this, you can either do the angle where they were reflected, or you can do its vertical angle, whichever one's easier for you. I'll do the vertical because it's out here where there's not other stuff. And when I do that, I get about 46. Hey, that's weird. It's odd that it would come out so great. Let's look here. If you did one, it would be unusual for it to come out just perfect, but it did, which is great if you're very particular about it. Your right angles as you do things make a difference in this. And so what I have here is what is the rule, which is reflection over two intersecting lines is the same as a rotation, and the measure of the rotation is twice the angle that the intersecting lines make. So that's a theorem as well. Here we have reflections in intersecting lines. Make a note of this So our two theorems for today have some commonality to them. The first one, we had parallel lines, two reflections made a translation, and the distance of the translation was twice the distance between the mirror. Two reflections on intersecting lines makes the same as a rotation from first to last, and the amount of the rotation is twice the angle that the intersecting lines make. So there's a little commonality there. So a summary of some of our theorems here that we've talked about this time and last time is that all of these are isometries. In other words, all of them, the copy is congruent to the original. When you make a translation, it's congruent to the original. A reflection and a rotation, those are called isometries. And what we have new today is that if you do more than one of them at the same time, the composition of two or more transformations that are isometries results in an isometry. And here endeth the lesson.